It's just carbon. Same stuff in pencils and barbecue charcoal. But under the right pressure and heat, it becomes something priceless. So how does that happen? And how are we now growing diamonds in labs, one atom at a time? Let's break it down. Part 1. The birth of a natural diamond. To understand natural diamonds, you have to go where no human has ever been, about 150 to 200 kilometers below the surface of the Earth. The pressure is crushing, and the heat is relentless. We're talking over 1,000 degrees Celsius, with pressures more than 50,000 times what we experience at sea level. Down there, carbon atoms start to rearrange themselves. They don't form flat sheets like graphite. Instead, they link up in a tight, rigid lattice. That's the beginning of a diamond. But that crystal still has to make its way to the surface. That's where volcanoes come in. Millions of years ago, rare eruptions blasted through the Earth's crust, carrying chunks of the mantle with them, and inside those chunks, diamonds. If the journey had been slower or hotter, the diamonds would have turned into graphite. But the speed of the eruption locked them in. The result? Vertical formations called kimberlite pipes. This is where diamonds waited for millions of years to be discovered. Part 2. From rock to rough. Once geologists discover a kimberlite pipe, the digging begins. Blasting equipment and massive drills carve out pits. At the Diavik mine in Canada, for example, they remove thousands of tons of volcanic rock a day. That rock is loaded onto 240-ton trucks and hauled to a processing plant. Inside the plant, those boulders are crushed into pieces just over an inch wide. The goal is to free any diamonds hidden inside without damaging them. It's a delicate balance. The crushed rock goes through grease tables, dense media separation, even X-ray sensors. Why grease? Because diamonds repel water, but stick to fat. While most of the crushed rock washes away, the diamonds hold on. The result is a batch of rough, uncut diamonds. Most won't end up in jewelry. In fact, only about 20% are clear and perfect enough for that. The rest go into drill bits, laser optics, cutting tools, and other industrial uses. But natural diamonds aren't the only way to get the real thing anymore. Let's go inside the lab. Part 3. Growing a diamond in a lab. Now, when people hear lab-grown diamond, they usually think of jewelry. But here's the thing. 99% of diamonds made every year aren't for rings or necklaces. They're for machines, drill heads, engine components, 3D printer nozzles. At a place like US Synthetic, one of the world's biggest industrial diamond factories, they're not growing gems, they're growing tools. It starts with diamond dust. Literally, microscopic particles of synthetic diamond powder, the same stuff used in grinding wheels or cutting saws. You can actually buy a little bag of it online for 15 bucks. But turning that dust into a usable diamond takes some serious force. First, the powder is spooned into a tiny metal mold, just big enough to fit on the tip of your finger. Then a base is added, a small disc of tungsten carbide soaked with cobalt. This is what the diamond will grow onto. Now comes the fun part. That little metal capsule gets packed into a salt sleeve and surrounded with compressed talc. All of that gets loaded into a 6-piston cubic press the size of a garage. The machine squeezes with over 1 million pounds of pressure per square inch, the same as stacking 100 elephants onto an ice cube. But pressure isn't enough. You also need heat. Electrical contacts hit the top and bottom of the mold, and the metal shell inside turns into a resistive heater. It climbs to 2,500 degrees Fahrenheit in seconds. Inside that metal canister, a few things happen at once. The heat starts melting the cobalt inside of the tungsten. That molten cobalt seeps up into the diamond dust and acts as the catalyst, helping the carbon atoms realign into a solid crystal structure. That's the moment the diamond begins growing. The entire process takes just 10 minutes. In that time, what started as loose yellowish powder transforms into a single, jet black polycrystalline diamond. It's not shiny yet, it's not even visible. It's still sealed inside the mold like a baked cake in a cast iron pan. Once the press is done, the team breaks open the talc, slices apart the salt capsule, and pulls out the metal thimble holding the new diamond. To get it out, they hit it with a sandblaster made of silicon carbide, a level 9 on the Mohs hardness scale, but it doesn't leave a scratch, because the thing inside, it's a real diamond, a level 10. At this stage, the diamond is still fused to its tungsten carbide base. That's on purpose. For drill bits, cutters, and bearing components, the tungsten acts as the mounting surface. If needed, they can grind it off to leave just the diamond itself. That's how they can make things like industrial 3D printer nozzles, solid black diamond tips that last virtually forever, even with abrasive materials like carbon fiber or glass-filled filament. And just to prove it's legit, they do a scratch test. Level 9 pick, no marks. Only a diamond can scratch a diamond, and this one passes with flying colors. The whole point of using polycrystalline structure, tiny diamond crystals fused in random directions, is toughness. Not just hardness, but impact resistance. A single crystal diamond might be clearer, but it's also more brittle. This black diamond? It's the Lego bricks welded together at the atomic level. Nothing on Earth can chip it. Once the shape is right, the diamonds go through CNC polishing using more diamond dust. There's no shortcut here. The only thing that can polish diamond is another diamond. But the result is perfect, engineered diamonds tough enough to drill into oil wells, power satellites, or print components for spaceflight. Part 4. The final cut. Whether the diamond came from the ground or a lab, it doesn't look like much at first. It's dull, cloudy, and misshapen. But inside that raw stone is a perfect gem waiting to be revealed. This is where the artistry comes in. Using 3D scanners and computer models, cutters plan the best way to slice the stone. Every decision is about balance. Maximize carat weight, but don't sacrifice brilliance. Avoid internal flaws. Keep the best angles for reflecting light. Lasers make the first cuts. Then, diamond-tipped polishing wheels refine the shape. Each facet is added with microscopic precision. The classic round, brilliant cut? That one has 57 or 58 facets, depending on whether the collet, the bottom tip, is polished. Once the cutting is complete, the diamond is cleaned, graded, and certified. Now it's ready for a ring, a pendant, or maybe a microscope lens, depending on its clarity. Natural versus lab-grown. So what is the difference? Chemically and physically, there isn't much. Lab-grown diamonds are just as hard, just as sparkly, and just as real as the ones pulled from the earth. What's different is time. Nature takes millions, even billions of years to make a diamond. Labs do it in weeks. Then there's the price. Lab-grown diamonds are often 30 to 40% cheaper. And since they don't involve mining, they're marketed as more sustainable and more ethical. But not everyone agrees. Some jewelers insist that a natural diamond has something a lab diamond can never have. Age, history, a story that started long before humans even existed. Others say that lab process is the future. It's cleaner, faster, and better for the environment. And if you can grow the same thing for less money and less destruction, well, shoot, why not? Both kinds of diamonds still end up in rings, in tools, in satellites, and surgical lasers. Both come from carbon, and both are shaped by heat, pressure, and time. It's what happens when you push the simplest element on Earth to its absolute limit. You get something rare, something durable, something that catches light and never lets go. Thanks for watching. If you enjoyed this deep dive into the world of diamonds, be sure to hit that like button, share it with someone who loves science or sparkle, and subscribe for more stories from the hidden side of everyday things. See you in the next one.